Once again, I'm here. Now we are here to actually look at another interesting subtopic under physical quantities. We have dimension and dimensionless quantities. Now, for dimension quantities, as you can see, dimension quantities, these are quantities which can be expressed in terms of dimension of two or more fundamental quantities. And we have examples include, we have area, volume, force. There are many. They are many. I can tell you that. Now, this dimension quantity, I'm going to, when I get to dimension analysis, you're going to understand better what I'm trying to talk about. Now, let us go to dimensionless quantity. Now, for dimensionless quantity, we have that what? These are the ratio of two quantities that have same units. They do not have units. I will explain. Now we have the example refractive index, we have the relative density, and we have the relative permittivity. Meaning that what is just, let me just give you a very little example from what they are saying. Now let us take relative permittivity. Now, relative permittivity, we have what? The permittivity of what? A free space over what? The permittivity of a medium. Now, looking at this now, is, the permittivity of the medium over the permittivity of the free space. Now, from this, let me explain a little, let me take you back to what? A particular topic that you might not understand, but I want you to follow me. Now, we have what? In force, in Coulomb's law, we have F equals to KQ1, Q2 over what? R squared. And we have the unit of this to be what? We have our K. Our K equals to what? 1 over 4 by epsilon. Now, in this sense, now from here, F equals to what? Q1, Q2 over 4 pi epsilon R squared. Now, we can make our epsilon naught here, which is the permittivity of the free space. It's a very interesting topic. Now, if it has units, let us assume for your stage now, let us assume that the permittivity of the free space has Newton and meters. Now, permittivity of a medium also have the same kind of units. So we have the permittivity of relative permittivity, is what? The permittivity of a medium, let us say, is 5 Newton meters. I'm just assuming, So for permittivity of a free space, let us say we have 2 Newton meters. Therefore, if we cut it out, you notice that what? This relative permittivity here has no unit. That is why it says these are the ratio of two quantities that have the same unit. It's a ratio of two quantities that has the same unit. They do not have units. Example, we have a refractive index, relative density, and what? Relative permittivity. Now, for relative density, we know that we are relating what? The relative or the density of a particular material with what? Water. So it will not also have unit. Now that takes me to dimension analysis. Now, for dimension analysis now, we are going to be considering how we can find the relationship that between the quantities in a dimension way. Now, we have that what? Dimension is a quantity which is expressed in terms of dimension of two or more fundamental quantities. What are they trying to say there? Don't be confused. Now, we have what? Our fundamental quantities. We have our fundamental quantities. Now we have their symbols. and we have what? Dimension. Now, for fundamental quantities, now, for your level, let me put it that way. For your level, we are going to be looking at just 4 of them. Now, we are going to be having mass, length, time, and temperature. For your level. So, how can we express all these 3 fundamental quantities in dimension quantities? Now, we have the symbol for mass as what? Kilogram. For length as what? Meters. For time as what? Seconds. For temperature, we have it as what? Kelvin. So, as K, K. Now, what is the dimension? Now, for dimension, we use the capital letter of the word, the first letter of the word. So we have the mass. What's the first letter? Then we have M, capital letter M. For length, we have what? L. For time, we have what? T. Now, we have what? Temperature having T also. Now, for dimension, we don't use T, but we use what? Theta. So, these are the what? Dimension. In order to express all these fundamentals, we can express it in dimension. So, now, let us look at example. From the example I gave to you the last time, I said area equals to length times breadth. And I told you that about the basic unit for this is meters times meter, which is what? Meter squared. Now for dimension now, let us look at the dimension. Now for length, we have length having what? Capital letter L. And we have what? Our breadth also meters. And here we have it as what? Capital letter L. Then we have our dimension as what? L squared. You can't escape these kind of questions. So you have also, let me look at another one. Let us go to volume. Simple length times breadth times what? Height. So you have that, the basic unit, let me shorten it, as what? Meters times meters times meters, which is what? Meters cubed. But in dimension now, will be what? L times L, which is what? L cubed. As you can see. Now we can also have, let me take it a little bit complex. Let's go complex. Velocity. Velocity is what? Your displacement over what? Time. And your basic unit here will be what? Meters over seconds. From what I explained the last class. Now, let us change it to dimension. So you have what? L over capital letter T, which is what? LT minus 1. So you can have this for as many quantities you can think about. You can have these written there. So I want you to take this as an assignment. Write out the following in, I'm very sorry. Write out the following, physical quantities in dimension. For those of you that may be finding it very difficult to see my handwriting, you can actually follow what I'm saying too. So write out the following physical quantities in dimension. So we have that what? 1, pressure. 2, force. 3, density. 4, momentum. 5, impulse. 6, there are many. 6, we have I would like to make it a little bit very difficult, but it's not difficult, mind you. So we have impulse, speed, okay, we have, let's take this down, resistance, yes, resistance. This one is a little bit very tricky, but it's not still difficult. You can take your time to actually answer. Let me give you an hint of what I'm expecting from you. Let us take a particular example like power. We said power, example, so that you should know what I'm actually expecting from you. Your power is equals to what? Energy over time. And you know that your energy is also same thing as work done. So we have that what? Oh, okay, let me give you number 7 as work done. Sorry, work done. Although I will do it here, so I just want to give that as a bonus. So we have work done to be what? Force times distance. Let me write it full. Now, we have force times distance to be our work done, and we have our force. Our force is what? Mass times what? Acceleration. Times what? Distance. Now, let us break it down. We have the basic unit of acceleration and mass and what? Distance. What are the basic units? Is what? kg, meters per second square, and we have what for distance? We have meters. So let's try to add mathematics. That's what? M over x squared times m. So I will try to go up there so that you can. So we have kg multiplied by m over s multiplied by m. Now, you have m multiplied by n to be what? kg multiplied by m squared over, sorry, this one is square, s squared. So therefore, we can say the basic unit for work done alone, work done, the basic unit is what? Work done, basic unit is what? kg meter square s minus 2. We have that as a basic unit for work done. But we can actually simplify it. The dimension will now be what? See what I'm talking about? So that you should have an hint. I want you to replay it again so that you can have an insight of what I'm trying to talk about. Now, what will be the dimension? Let's go back to the table here. Now, from the table we have kg. Kg is having what? Mass. M. What is M? Length, meters. We have what? Capital letter L. So M comes here and change to what? L in dimension. You have square. The square still follows. Your S is what? Seconds. And in dimension is what? T. Capital letter T. Minus 2. So you have the dimension of your work done to be this. Now, but the main question was that we want to look for the power, the dimension for power. So we have our power to be what? Work done over time. Now, some people might be asking, why did I wrote down energy here, and also here I changed it to work done. Now, energy and work done are the same thing. Energy and work done are the same thing. So far, their units are also the same. The unit of work done is what? In joules. While energy is what? In joules too. We have energy to be defined as the ability to what? To do work. And work done is the what? First item. So before a work can be done, energy is actually in play. So we have that work done and energy, they are the same thing. When we get to that particular bridge, we're going to cross it. So now let us go back. So that will be what? Now what's the dimension now? The dimension for power. So will be what? What's our work done? We have what? N squared T minus 2. And our time now, let's go back. Our time is what? Capital letter T. So therefore, I can simplify this by saying that what? ML squared. Now this T raised power minus 2, you can bring it down to be what? T raised power 2 multiplied by T. So therefore, what do you have as your answer? ML squared over T cube. Take it all back. ML squared T minus 3. Answer. So the dimension for power there is what? ML squared T minus 3. Now, why did I actually do this for you? Is because you are going to be using that to get the dimension for resistance to make it so very easy for you. Just try to brainstorm. I'm very sure that you're going to get the what appropriate answer. Thank you very much. See you in the next class.